Welcome students. Today we will start blackbody radiation. When a thermal radiation incident on a body, then they are partially reflected. Let us consider here a body and the radiation is coming on them. Radiation is coming on them. Then it is partially reflected. Some of the part is reflected and partially absorbed. Some of the part is absorbed by the body and some of the part is partially transmitted. So, when thermal radiation is Q, that is Q amount of thermal radiation incident on a body in a given time, then R is the thermal radiation reflected by the body in same time, and A is the amount of thermal radiation absorbed by the body in same time. T is the amount of thermal radiation transmitted by the body in same time. Then for energy relation of radiation, the Q is equal to R plus A plus T. Now we define some terms. The first is reflectance. As the amount of the heat radiation Q is partially reflected, then the reflectance of a body is defined as the ratio of amount of thermal radiation reflected by the body in given time to the total amount of radiation incident on the body in that time. So capital R, that is radiation which is reflected, and capital T, Q, that is total amount of thermal radiation. The ratio is represented by small r and it is called reflectance. Same time, some of the amount of this radiation Q is absorbed by the body, and we are representing it by capital A. The absorptance of the body is defined as the amount of thermal radiation absorbed by the body in a given time to the total amount of thermal radiation incident on the body in the same time. So absorptance is represented by small a. Next is the transmittance or transmitting power. Some part of the radiation is transmitted to other way from the body, and it is represented by capital T. The transmittance of a body is defined as the ratio of amount of thermal radiation transmitted by the body in a given time to the total amount of thermal radiation incident on the body in the same time. So, the transmittance T, which is represented by a small letter of t, will be capital T upon Q. So, it is transmittance. As we earlier find the heat radiation Q is equal to R plus A plus T. And if we divide this equation by Q in both sides, then Q by Q will be equal to R by Q plus A by Q plus T by Q. Q by Q is 1, and capital R by Q is reflectance, that is represented by a small r, and capital A by Q is absorptance of the body, represented by A, small letter a, and capital T by Q is the transmittance of the object. So we will have an equation R plus A plus T is equal to 1. Now coming on the important point, that is black body. If perfectly black body absorb all the radiation of every wavelength incident upon it. If we say we have an object which absorb all the radiation, it means the reflectance is 0, the transmittance is 0, only there is the absorptance, then the absorptance A will be equal to 1, because we know reflectance plus absorptance plus transmittance is equal to 1, and R is 0, T is 0, so the absorptance is 1. This type of body which have absorptance 1, it means it absorbs every radiation of every wavelength. And this type of body is called perfectly black body, and it is a theoretical concept. Since a perfectly black body neither reflect nor transmit and nor radiate, so absorptance is unity. It has no reflecting power. At normal temperature, because it has no reflecting power. So if we see this object from other side, so it will appear just black, because it has no reflecting power, irrespective of color of radiation incident on it. Now this is the black body. Whatever the wavelength of the incident radiation, whatever the wavelength of the incident radiation, it absorbed by the body. So there is no reflection. So this will appear just like as a black object. If a perfectly black body is heated, now if we heat this black body, then what will happen? This black body, whenever heated, it will radiate the energy. And the radiated energy from this perfectly black body will have all the wavelength which are possible. So lambda, the radiation wavelength, will be 0 to infinite. Radiation emitted by the perfectly black body are referred to BlackBody radiation. Whatever the radiation emitted by the black body is called BlackBody radiation or full radiation, because the range of wavelength will be 0 to infinite. Or this is also known as temperature radiation. As we know, this is a perfectly theoretical concept. So we only can make some arrangement for a perfectly black body, and that arrangement is called Fairy's black body. A cavity with wall made of any material with a small opening can act as excellent black body. Here is the figure of Fairy's black body, having a very small opening. Here is the very small opening, and this opening is represented by N. And the radiation is incident inside this hollow doubled wall metallic sphere. It has double wall. First wall outside and the second wall is inside. Having a narrow opening and conical projection just in front of this hole. Here is the conical projection. From inside the sphere, a coated with lamp black. Now this double wall metallic sphere, the inner wall is coated with lamp black. So lamp black will absorb the light radiation. But we already say we haven't such a perfect black body. The lamp black will absorb only 97% of the radiation. So its absorptance of lamp black is 0.97. It means the 3 part of the radiation will reflected by the surface. The incident radiation will fall on the inner wall, then some part of the radiation will reflect it. That is only the 3%. And after the reflection, it will fall on the other side of the wall. It will also absorb the radiation. So the radiation which reflected becomes smaller and smaller in amount, and it will always engaged inside the hollow double walled metallic sphere. So we can say this double walled metallic sphere, which is also known as fairy black body, is a perfectly black body. The radiation entered the opening from outside has little chance to escape. That's why we are calling it perfectly black body. If this black body is kept in a bath of fixed temperature, the heat radiation comes out of the hole or opening. Now what is going on? If we are taking this fairy black body and we are heating them, then the radiation will come out from the black body. This radiation which comes out from the black body will be having all the wavelength. Thus the opening is enclosure act also as blackbody radiator. Now we will consider some definition here. The first one is the monochromatic emittance. It is also called spectral emissive power of a body, corresponding to the particular wavelength of a particular time. So the object is radiating the wavelength, and this wavelength is from 0 to infinite. Now for a particular temperature, the temperature of the system is taken as T. This radiation energy emitted per unit surface area per unit time. The area of the body is unit and the time is 1 second, that is unit time, within the wavelength of lambda by 2 to lambda by minus 2. Because it is radiating all the wavelength and we are considering the radiation lambda by 2 to minus lambda by 2. That is, the range of wavelength is unit wavelength. The total emittance or emissive power of the body at a certain temperature is defined by total amount of thermal energy emitted per unit area per unit time for all the possible wavelength. Now if we are considering this wavelength is from lambda by 2 to minus lambda by 2, then it is represented by monochromatic emission of wavelength E lambda, that is spectral emissive power. But this wavelength, this emission is from 0 to infinite, not a single wavelength. So the total emittance will be represented by E is equal to integration 0 to lambda monochromatic emission E lambda integrated with respect to wavelength. So this is called total emittance. Its SI unit will be watt per meter square or joule per meter square per second. It is energy per second per meter square. Now this is for complete range of wavelength. Similarly, for monochromatic absorption, if the object is a black body and the radiation is absorbed by the black body and its wavelength is also from lambda by 2 to minus lambda by 2 range, means that range of wavelength is lambda. So we are again considering a unit wavelength. The spectral absorptivity of the body corresponding to a particular wavelength at a particular temperature is defined as amount of absorbed energy per unit surface area of the body per unit time within unit wavelength. Interval around wavelength lambda is between lambda plus half or lambda to minus half. Its unit will be same. It is also watt per meter square. Now next point of interest is Kirchhoff's law. The ratio of emissive power, that is emissivity, to the absorptivity corresponding to a particular wavelength at a particular temperature is constant. So for a particular wavelength, the emissivity or emissive power is E lambda and the absorptive power, that is spectral absorptance, A lambda, is a constant. So according to Kirchhoff's law, the ratio of emissive power to the absorptive power corresponding to a particular wavelength at a particular temperature, it means the temperature is also constant here. So we are defining E lambda by A lambda at a particular temperature is constant. And this law is called Kirchhoff's law. And this constant is represented by capital E lambda. It is also known as emissive power. The emissivity to the absorptivity is constant and it is called emissive power of a perfectly black body corresponding to a particular wavelength at a particular temperature. So E lambda is equal to constant into A lambda, or simply E lambda is proportional to A lambda. It means the good emitter good absorber. So Kirchhoff's law can be said the good emitter of radiation are good absorber of radiation or vice versa. That is good absorber of radiation or good emitter of radiation. For a perfectly black body, E lambda will be equal to A lambda. For a perfect black body, the emissive power will be 1 for a particular wavelength. Here we have 4 containers were filled with warm water. First is of shiny metal, the second is of dull metal, third is of dull black, and fourth is of shiny black. And the warm water is filled on them at the same time. Now if we discuss about the temperature of water after 10 minutes, the container having shiny metal would have the warmest after 10 minutes because its shiny surface reflects heat radiation into the container. Now the water which is inside here, the warm water, it is reflected by the shiny metal and it will remain inside the radiations remain inside the container of shiny metal. So it will be warmest after 10 minutes as it is losing very small amount of heat. The container of dull black will be coolest because it is the best at emitting heat. According to Kirchhoff's law, this is a black body. It will absorb the radiation. It will have a best absorptivity. So it emit the heat radiation largest. So the temperature of dull black water will be coolest. This is emission experiment where the radiation is emitted. The shiny metal emit least radiation and the dull black metal container will emit the most radiation. Now we have the 4 containers again. They are placed at equidistant from a heater. Now we have a hot bath here and the heat is given to all these 4 containers. Heat is given to all these 4 containers and they are equidistant from the hot bath. The dull black container would be warmest after 10 minutes because its surface absorbs heat, having a very good absorptance. And the shiny metal will not absorb as the others because it will reflect the radiation. It will reflect the radiation. So the shiny metal will be coolest because it is poorest at as absorbing heat radiation. On measuring the temperature of these four containers in both the experiment, we will say the good absorber are good emitter or vice versa. The bad absorber are bad emitter. The statement is called Kirchhoff's law. Thanks all for watching the video.